So I have a few updates to share with you all. We still have our test on Wednesday. So I want you to kind of think of if you did well on the first test, just kind of continue going. If you didn't do well, think of this as a reboot, because remember that first test will be replaced by a higher score on the final. So do well on this particular exam, and we could just say that this is where you start, right? This is where really your grade will start. As far as the homework, it's currently due on Wednesday, the day of the exam. What I will do is either today or tomorrow morning, I'll move them through the weekend, because I don't want you focusing on maybe those last two, whatever, if you've got some left in there. I'd like you to be able to finish it, but what I want you to focus on is the exam review. And specifically, at a minimum, the questions we're going over in class. So we went over 5 questions from Chapter 3 on Friday. Those are recorded and they're listed. And then we will do 6 questions from Chapter 2, kind of going back over some of those. The other thing is thinking ahead. In about 2 weeks, we have our mastery exam, and I've got a copy of it. What it is 20 functions that you will take the derivative of. No word problems, nothing, just functions, take the derivative. Product rule, chain rule, quotient rule, implicit, any type of derivative we've done is on there. There's 20 questions. They're all multiple choice. So all you have to be able to do is recognize the correct derivative. And that's all it is. So it's kind of making sure you're able to take derivatives. Everything we've got up to today is all you could take it today, literally. Not maybe you don't feel like it, and we won't have to, but all the content that you need for that mastery test we've gone through it. So that's why also, if I give you that extra time to go back and maybe finish up the little pieces on any of the homeworks from previous through the weekend, that'll be helping you get ready for that mastery test. We'll go into sections. The early part of Chapter 4 is still derivatives, looking at using derivatives for maximum, minimums, and sort of applied problems. And then we get into integration, which is derivatives backwards. So they give us the derivative and we have to find the original function. That's what an antiderivative is. So we'll keep moving forward.
Is the mastery test weight the same as the chapter test?
It's half of a chapter test. So we'll have the 3 tests, and the mastery is only half of one of these tests. And like I said, it's just here's a function, get its derivative. So all the techniques we've used. And there's a review for it somewhere. I haven't located that, but I'll have that up and running by the weekend. So if you want to start looking at that, but for now, we want to have you focus on the review. And today, we want to focus on Chapter 2. Because, and just to reiterate, the exam is really, the format of it is just like last time. 8 multiple choice questions, 3 open-ended essay-type questions where you need to show your work. I did highlight them, so I'll do them again. So the free response, there's 1 related rate problem, 1 linear approximation, which we'll do one of those today, and we'll do one of the related rate problems as well. So we'll do two of the types of problems that will be on the free response portion we'll do today. There's 1 on L'Hopital's rules, so know how to, again, do that in an essay format. So you just set it up, remember, make sure that the limit's 0 over 0 or infinity over infinity, take the derivative and go from there. And then there's 4 questions from Chapter 3. We talked about those: logarithmic differentiation, expanding logs, to take the derivative, inverse trig derivatives, and derivatives using Theorem 7. So we did those on Friday. Everything you need is under review for exam 2. There's 2 other little review things, but what I did is I copied them over here. So there's focus on Chapter 2. This is a copy of the Word document I'm going to use today to work through the problems we're going to work through. Everything we did on Friday from Chapter 3 is down here now, and here's the recording of Chapter 3. So you could go back and review that. And so if there is nothing else, and then up here is the exam review itself. It's the one that was on the department website. It's got the answers right under the questions in bright red. The ones I'm going to be using, I've taken out the answers so it's a little less distracting, but we can always go back and take a look and check your answers there. So you've kind of got both formats. So let's go. Actually, I don't need that. I've already got it downloaded. I've got it right here. Let's go with this. So we'll go through a quick little review of what we did in Chapter 2. We started off with the product and quotient rule. Seems like that was maybe so far along, but that's what we started with. So there's also a form of sort of derivative formulas, all the derivatives we've taken, thanks to the teacher before us. She came up with a sheet, and I just asked her if I could have it. She let me have it. So I've got it here. The only thing I added is for the product rule and quotient rule, I put it so it's easier to remember, because this is the way I can remember it. If I go the way it's put in the textbooks and everything, one's kind of backwards from the other, and I mess up, as you may have remembered during the lecture. So you can use either my handwritten version or the other version. They'll both work, whichever works best for you. So that was pretty much Chapter 4. Chapter 2.4, 2.5, we looked at the chain rule. So it's the derivative of the outside function with the inside just kind of sticking in there, and then times the derivative of the inside function. So we apply that a lot. 2.6, we picked up implicit derivatives. So that was when there was both an x and a y, or even, as we saw later, maybe a third variable, t, time was involved. That's where we use implicit. Oh, yeah. So you can download all this, right? Because it's in Canvas. In fact, there's a whole sheet that has this is the bottom of the sheet, and above it actually gives all the rules for taking a derivative, constant rule, logarithm rules, everything. Trig rules, all the trig derivatives are all there. So it's pretty good. And I just took a little stamp here, mainly for these ones that we have here. Okay. So implicit derivative, every time we take a derivative of a y, it's dy dx. Take the derivative of x, it's just like normal. So we'll do some of these. And then actually the next two sections rely on implicit derivatives. Okay, our applications of implicit derivatives. 2.7 was related rates. And I just thought maybe to get a visual, there's two different rates, and we started with the ladder, and actually one side of the ladder is moving at a faster speed than the other. And so but it's related to the bottom rate, how fast that's slipping. And so we could find the two rates. And remember, that's what a derivative is. It's a rate of change. It's a slope. And so we're seeing how the change in y is related to the change in x, but it's different. They're not always the same. So that was one example we took a look at. Here we go. And then we did linear approximation, which again was sort of like implicit derivatives, where we could think of the dy and dx actually being two different parts, being a change in y and a change in x. So we've got a problem to take a look at today that applies this one as well. And there's a little drawing. So each one was kind of, one little concept, but we worked a lot of different examples along the way. And so what I wanted to do is focus on the types of questions that'll come up, get you ready for the exam. I got the results back from the coordinators collected all sections, how they did on the first test. And basically we came up with about what everyone else is doing. There's a median score of about 79. I'd round that maybe to say 80 by the time we're done. So the median score was a B, if you look at that. So that means half of you got a B or better, half did. But again, those half that didn't, look at this as a restart. right? We'll do well on this one. We'll just start counting from here, and then we'll forget about that first one ever happened. Okay? But it was a learning experience. But we're right on track with what's going on in all the other sections, and I didn't count, there's 7 or 8 of them, so that reported. Okay, so this is one type of thing you need to be able to do is take a derivative, and the information we're given is we're just given this table that tells us, we don't have a function, but what we have is we have values for f and then values for its derivative. So these two columns go together, and then we have the g function, and we have the values for its derivative. Okay, so these are designed to see if you know sort of the formula for doing the product rule, the chain rule, the quotient rule, and we'll actually do all of them. The question that you were given for the practice just has the product rule, but we'll also do one with the chain rule just so you can see. We're going to use that format, but we get our answers from going up and looking in the table. Okay, so to get the derivative of h, which is a function of f and g, what we're going to do is use the product rule that we take the derivative of f times g, and again, since we're doing it at a particular point, each of these will be at that x value, and then we add the derivative of g at 2 times the function of f. Okay, so just kind of laying it out there, that's the product rule formula. So the derivative of f at 2, I come here to this column. When x is 2, y is going to be 3. So I put that in. For the g function, I come here, and so I look when x is 2, the output value is 4. And then I look for g prime, the derivative. So when x is 2, the derivative is 4. And then I look up the f function when x is 2, here it is, y is going to be 3, and now it's just an arithmetic problem. So it's 12 plus 12 should be equal to 24. Okay, so we'll be able to do that one. We can also apply this if we would have had a quotient rule. So maybe f of x over g of x. And again, that will be similar. And I always, that's why I kind of change it. I take the derivative of f at 2 times g at 2. Up, not plus, it's minus, right? So here we go. Let's see, where were we? So derivative of f at 2 times g at 2 minus derivative of g at 2 times f at 2 all over g at 2 squared. Okay, and again, it's just looking it up, and we've kind of done that. The derivative of f at 2 is 3. G at 2 is 4. Minus the derivative of g at 2 is 4. The derivative of f at 2 is 3. All over the derivative of g, or not, the original function g at 2 is 4, so that's going to be 4 squared. We get 12 minus 12, so we get 0 in the top, which makes it kind of nice, and final answer 0. Okay, but there's a couple places where we have it. There's in the practice test, there's one, there's also, I think there's one where they use the chain rule and have a table. And again, you look those up. Okay, doing okay? Okay, give myself more space this time. Now this one, I'm not sure we ever did one like this in class. In fact, I would almost say we didn't. But it's an important one to have, is remember, we did talk about the derivative of trig functions kind of being circular, that it will start repeating. And so what that does is it allows us, we don't actually have to sit here and take 28 derivatives, although you could, but you're going to see what we'll do is we'll take maybe 3 or 4 until we see a pattern, and then we'll be able to figure it out. So that's what this one's about. So what we're going to do to find the 28th derivative, well, let's just start taking derivatives till we see a pattern. So I'll take the first derivative is going to be y prime equals derivative of cosine is minus sine of 4x. And is that it?
Negative.
There's a 4 that comes off. So then we take the chain rule, take the derivative of 4x. Derivative of 4x is 4, so we multiply by 4. We could put it on the back side, but what we're going to see is we'll just put it here. Okay, we could move it to the front. So minus 4 sine of 4x. Okay, good. When we take the second derivative, what are we going to get? Well, derivative of sine is cosine. Then minus 4 just comes along for the right. It's a constant multiplier out here. 4x is inside the function. Nothing happens to it, but derivative rule, chain rule, we get another 4 coming off, right? Derivative of 4x is 4. So we're going to multiply by 4 again. So how could we write this? Well, we could just put this as 4 squared. You could put 16, but you're going to see the pattern much easier if we just, because that's going to keep happening. Each time we take that derivative, we're going to get another 4 coming off. And that 4 and 4 squared in front are just going to keep coming along. So the third derivative, y to the third. Again, what's the derivative of cosine? Negative sine. So that negative and negative become a positive. I'll go ahead and put a plus just to emphasize. We still have that 4 squared, but before we get there, I'll put this 4x. We're going to get another 4 coming off, because chain rule, when we take the derivative of 4x, we get 4. And we have 4 times 4 squared is going to give us 4 to the third. Okay. Have we started to repeat yet?
Yeah.
Almost. Good. We see a sign of 4x in there, but one's negative, one's positive. So let's see, did I mess up? When I was doing this at home, I did the wrong, but let's just see. Let's see, y to the fourth derivative. So derivative of sine is cosine. 4x, oops, squeeze that in. And then we get a 4 coming off, so that's going to be 4 to the 4th power. And it's still positive. And now we see we started with cosine to the 4x, and now we've gotten back to cosine to the 4x. So it takes 3 derivatives, and then on the 4th one we start repeating, right? So that's kind of how it is. So 3 derivatives, and then the 4th one will repeat. I didn't mess up, did I? Oh, okay. So then what we've got to think, okay, what would I get? 28. So it's kind of got a cycle of there'll be 3, and then it'll be the next one, right? Will be whatever we started. So what you can see is that the number in front is 4 to the power of whatever derivative it is. So we could say when I get down to the y to the 28th derivative, we're going to have 4 to the 28th power. Does that make sense? And then we just got to figure, is it going to be a sine or is it going to be a cosine? Let's see, it takes 1, 2, 3, 4 derivatives. I'm back to cosine. So if I do 28 divided by 4, that means I've gone through 7 full cycles. So I would have gone through, I would be back here at the end here, so it's going to be a cosine, and it's going to be a positive cosine. Not bad. Now, if we wanted to go to the 29th, it would have been 7 full cycles plus then whatever would be occurring next. And so we've got enough pattern to say that, well, the 29th one will be -4, or, you could go from there once you got it. So figure out how many times until the cycle repeats. Divide that, because you don't need to keep doing the same cycle again. You just need to find out where in that cycle of 4 full derivatives to get back to the start. Okay, so a little bit of work, but not too much. Just don't fall asleep at the wheel. I did that when I was doing this. I had 2 cosines in a row, and I go, wait, I didn't do that quite right. I was trying to go too fast. Okay? So be able to do that. And here now we're going to get into implicit derivatives. And this one says find the slope of the tangent line. Remember, the slope of the tangent line is just the derivative. So the question might ask for the derivative of dy dx, or it might ask for the slope of the tangent line. And so we've got this function here. And then we're also given a point. And again, on the test, you may be given a point, or you just may be asked for the derivative in sort of expression form. So we'll do both. We'll get it down to where it's sort of just an expression. It's just the derivative. We'll plug in the x and y coordinates and also get it down to a value, so we know how to do both of those. Okay. So what's the derivative of 5 sine x? So it's going to be 5 cosine x, right? So that's this part here. And then we've got a 4 cosine y. So when we take that derivative, what do we get? -4 sine y. And I like to put little parentheses, otherwise that messes up. And then since we're taking the derivative of y, dy dx. So we got that one. Then we've got a -4 sine x cosine x, and what does that indicate we're going to need to do here? Product rule. Good. So we're multiplying here. So the 4 will tag along, so we could go maybe -4. The derivative of sine x is going to be cosine x. Cosine y, nothing happens to it because that's the product rule. You only take one derivative at a time. And then we add, which might be a plus or a minus, we'll see. It's going to get us a -4, but this time we take the derivative of cosine. When we take the derivative of cosine, we get minus sine, right? So we're going to have a minus and a minus. We're going to have a plus 4 sine x. We didn't do anything to that. Cosine becomes sine y, or minus sine y, but we took care of the minus. And since we took a derivative involving y, what else do we need here? Thank you. Almost out of room, but not much left. Derivative of x, 1. Now just be careful, it's not 0, we can't just ignore it. It is actually, it's a constant, it's 1. Derivative of 7 pi, 0. Pi is a constant, it's a number. 7 pi is a constant, a number, so it's 0. Okay, now what do we do? We want to isolate dy dx. Now, I say that, but there's also, if we just needed a numerical answer, we could also plug in the x and y, and maybe it would simplify nicely without having to do too much algebra. They don't usually show us that, but it could be done. But we're going to, because they might want us to do one or the other, we're going to go ahead and do the algebra. So what I'll do is first is anything that does not have a dy dx, we're going to move it to the other side. So we're going to subtract or add it depending upon whether it's positive or negative. So that's got to go over. This has a dy dx. And this has a dy dx. This one in the middle doesn't. It's negative, so we will add it to both sides. And 1 does not have a dy dx, so we'll subtract it. So you're going to see all those will go over to the other side with those signs. And then I'll just rewrite this. So we're going to have this part here, minus 4 sine y dy dx. And then what other part? We have this part here, plus 4 sine x sine y dy dx. And then on the other side, we've got all this other stuff. I'm going to put the positive term first, so we'll go with 4 cosine x cosine y minus 5 cosine x minus 1. And then we want to factor out the dy dx, so we just kind of take it to the back or the front. I'll go ahead and put it in the back. And then what's left, all this other stuff here. And incidentally, on the open answer ones, if you've got the right answer and you've got overall the right steps, I don't get too deep into it whether you left off a line or a step or this or that, just as long as it has a flow. If you just have the answer and the, so be able to show some work, but what you end up showing is not, I don't get too picky. So then we have 4 cosine x cosine y minus 5 cosine x minus 1. And all this part here, we divide by it on both sides. So I'm just, instead of rewriting it all again, let's just put it, and again, maybe putting the positive side first. 4 sine x sine y minus 4 sine y. So we'll just say it got canceled out. So this is our dy dx over here. And again, a question might ask you for this. It's a multiple choice. You just got to match up with the right answer. It also might ask you to get a numerical answer. So that's where we plug in these, and that's where you have to kind of have at least the basic unit circle in mind. So we've got 7 pi and 3 pi over 2. Now 7 pi is what? It's 6 pi would get us around the circle 3 times and then 1 more. So we could actually get the same function values if we just look at that as being pi. And then 3 pi over 2 is going to be what, 270 degrees? So that's this angle here all the way around and pi. So they're both, the nice thing is they're either 0 or 1 depending upon the values, but by looking at these we'll see. So cosine of x is pi, so cosine is going to be -1. So we get 4 times -1. Cosine of y is 3 pi over 2. What's that cosine? 0, right? Cosine here is 0 because it's on the y-axis. So that's actually kind of nice. And like I said, sometimes these, if you do this earlier, a lot of things start simplifying out, because if we multiply by 0, that whole term's gone. So take that as a technique. If you're looking for just an answer, if the answer is looking for just a number, maybe input these stuff earlier instead of doing a lot of algebra. Then we've got -5 cosine of x, cosine of pi is -1, and then we've got a -1 here. Let's go up a little bit more. In the denominator, we've got 4 sine of x. X is pi. It's the y value. Y value is going to be 0. So again, that makes this one all disappear. We don't really have to look at sine of y, but we'll do it anyway. It's -1 because that's on the y-axis. And then we've got 4 sine of y. Uh-oh, we're in. So that's 4 times 0. And so what do we get? We get a 0 on the top. We get a +5 -1. And we get a 0 -0. So it looks like we get something that's like undefined, but that's okay. What's that? Oh, thank you. So pay attention, right? Half the time. Okay, so it's not 0. Sine of y. Thank you. I was wondering, why would this come up? But it could be. It could come up to be something undefined, right? So this becomes +4. So 4 over 4 equals 1. Okay. We okay with that? And again, we don't do any really fancy trig. It's going to be one of those standard angles. But at least know that first quadrant, those 3 angles. How are we doing? We're doing okay. Okay. Here's a related rate problem. This is from 2.7. And again, for this one, we will also use implicit derivatives. Now, this one, in the practice, they don't give us the formula for the volume of a sphere. On the exam, if they ask these type of questions, they will give you the formula.
What are calculators like?
And your calculators, I sure hope so. Yeah, please do bring calculators. Because the other thing is, a lot of these things, you can graph them and see what's happening, especially if you have anything with the limit, L'Hopital's rule type thing. Graphing calculators will be very helpful. So we've got the radius of a spherical balloon is increasing at a rate of 2 centimeters per minute. So that's a rate, right? I'm going to label that, since it's a radius, that's our dr dt. How fast is the volume changing? So the question is about the volume, dv dt, when the radius is 12 centimeters. So watch that one. When I was working this, I thought that was the volume, and I did a lot of extra work. I didn't. They're actually giving us the radius, so r equals 12. So we start with the volume formula. Volume is equal to 4/3 pi r cubed. Area of a volume. Yes.
Do we need to know the formulas?
No. They will provide them in the question. And again, because I was doing from memory, and I did the reciprocal. I did 3/4. I go, is it 4/3 or 3/4? Oh, let me try 3/4. I didn't get the right answer. It must be 4/3, and then it was right. So we don't want you to mess up just because you know. Anyway, so yes, they will give you the formulas. We'll use implicit derivatives because we're looking for rates, right? We've got our r here. So the dv dt, right, derivative of v, this is just implicit derivatives, equals, we'll just put it 4/3 pi, because that's a constant. Derivative of r, the 3 comes down, so we multiply by 3, subtract 1 from the exponent, so that's going to be r squared, and then we're using implicit derivatives, dr dt. So not bad. The 3's will cancel out, 3 divided by 3, and so it's really just 4 pi r squared. And we're given r is 12, and we're also given dr dt, that's 2. We plug those in, and we will have our rate of change of the volume. So dv dt is equal to 4 pi r squared is 12. dr dt is 2, and so that's 12 squared. Remember the details. Remember the details. 12 squared is 144, times 2 is 288. Yeah, good. And then times 4, 288 times 4. Not going to help me with that? 1,152. Thank you. Yeah. Pi. Now we could leave the answer like that. If they want it in decimal form, then we just multiply by pi. And this says to 6 decimal places, so we'd multiply by pi. I would use your pi key so that you get all the decimal places right. Okay, not just 3.14 is probably not, yes.
When we're multiplying by pi, does it specify what it wants us to use as pi?
It doesn't, but when they give you that it's going to be 6 decimal places, you better do it by at least 6 decimal places of pi. So 3.14 just wouldn't be enough. And I don't even remember, I think it's 1/6, but like I said, I got to 3.14, that's all I'm going to remember, and then I'm going to use my pi button on my calculator. Now if it's a multiple choice, it'll probably get you close enough, right? But we okay with that? Related rates. Okay. I think we got 2 more to go through. And again, these are the ones I would focus, these types of questions. There will be one for using linear approximation. And how do we go about doing that? So we could just plug 49.2 into our calculators. That's how we do it today. But what they did with linear approximation is they use a function square root of x. 49.2 is pretty close to 49, right? So that's the square root of 7. That's something we can figure out. But there's a little bit of what we'll call this as an error, a little extra change in x. And so what we're doing with linear approximation is we're getting the change of y. And so what we're going to do is we'll use the fact that if y was equal, if we were given the square root of 49, we know that that would give us 7. But we weren't given the square root of 49. We're going to see how the change of x results in a change of y. So we're going to take 7 plus whatever that change is. So we're going to take the derivative of both sides. So the derivative of y, derivative of square root of x, remember you got that negative 1/2, or that 1/2 that comes down, 1/2 x to the minus 1/2. So we could write this as y prime is equal to 1 over 2 square root of x. dx. Change in x, okay? And where that's coming from, I'm going to just scan up to the top part of the notes. That's really coming from here, that our change in y is the derivative times the change in x. Okay, the function value of x at the change of x. Oops. So what we're going to do is, what's dx? Well, we're going to say x equals 49, change in x is equal 0.2. We also talked about this being maybe like a measurement error, so it applies in the same places. So the change in y is going to be 1 over 2 square root of 49 times 0.2. Square root of 49 is 7. 7 times 2 is 14. 1 over 14 times 0.2. So then we get 0.2 over 14. That's going to be our change in y. And if you plug that in your calculator, you get 0.0. 1410. something like that? Oh,
0.0143.
0.0143, okay. What's that? 5 decimal places, yeah, if we could have 5 decimal places, that would be nice. So there's 3. One, 4, 3.
No, for 5 decimal places.
I got 0.0142.
Yeah.
29, rounding. So to 5 decimal places. And what do we do with this? Well, this is the change in y. If x were just 49, it would have been 7. So our answer really is, it's going to be y plus the change in y. So 7.01429. Okay. If you take the square root of 49.2, you'll see it's very close. It's about the 5th, I don't know, one of the decimal places it starts getting off, but it's a close, it's using really linear approximation because we're using that derivative to take this. Works fine as long as we're close. It wouldn't probably work very good to find the square root of 52 or something, you know. It gets further off. So is that okay? Linear approximation. So you'll probably be given some square root that's close to a nice perfect square. Kind of do that, and what you're doing is you're approximating that the number that we're given over here. I think one more. I think we're almost there. Yeah. So this is really the same. Yes, question.
I have a question. On the last one, what would make the derivative more accurate? Because I plugged in 7.2 and then did the square root of that, and I got 7.01427 instead of 9. So what would make, why is the derivative more accurate?
Well, no, you got a 7 instead of a 9. So this is off by, it's pretty close. Yeah, we got a 9. We're off by 2 10,000ths or something. Nothing. This method is about as good as you can get. I guess what you could do is use it to get the approximation to 49.1, and then maybe take that approximation so that you're just incrementally getting. You could get it as close as you needed, but this is probably, if you don't have an electronic calculator, you probably don't need more accuracy than that. All right. So this is the last one, and then we're good to go. So differentials, basically we just take this derivative as normal, and then what we're going to do is, the way I like to do it is dy dx, and then we're going to split the dy and the dx as if it were, as if they could be split, because they can. Okay, so I'm just going to take this derivative. The derivative of y is dy dx. Derivative of x squared, 4x squared is going to be 8x. And then the derivative of 7x is going to be 7. The derivative of 4 is 0. They give us, and this is 2 questions, they give us x and they give us dx. So we could plug it in at any point. What you're going to see is basically we could multiply both sides by dx. So that cancels, because all we want to know is what is dy. And so dy is, in the first case, 8 times 2 plus 7. Dx is 0.1. So that's 16 plus 7, 23 times 0.1. That's 1/10. That should be 2.3. And if they wanted the second one, you would do the same. Yes?
I thought it was like, it would be like dy equals like 4x squared dx over dx. Like, is that not like how it is?
You could. You could, because you could distribute it through. I just decided not to distribute it through. Notice I could have done that.
Yeah.
But I just said, since we're going to plug in numbers anyway, I try not to do too much algebra.
Okay.
Put the numbers in, and yeah. but yes, it would have worked that way as well. So yes, what he was saying is, could we just say that this is dy equals 8x dx plus 7 dx every time. So we put either a dx or a dy. That's another way to do this, and it would give you exactly the same answer. So you could do it that way. I like because we mostly using dy dx, and then we just treat dy dx as if it were a fraction. Okay, and so for the second part, we, since x is still 2, dx is 0.2, we get the same number, but it's 2.3 times 2 is 4.6. Okay. So know how to do those at a minimum. Focus on those. Remember, the homework will get moved over the weekend to Sunday night, so you can finish up anything that hasn't been finished. Focus on the exam, doing well. You've been through it. We'll do the same type of thing we did last time. Did that work? Pretty good.